Gracias por asistir al evento de hoy. Hoy tenemos unos invitados que van a presentar sobre Machine Learning. Como ya dije, pues este webinar es parte del Spanish Speaking Acoustics in the Americas, que es un capítulo regional de la ASA. Y después de una pequeña introducción en español, la charla será presentada en inglés, así que esperen y vamos a decir cómo pueden escuchar el audio en español. Bueno, este webinar es Machine Learning en clasificación y rastreo para acústica subacuática por Dr. Barnard de Penn State University, Dr. Timothy Havens de Michigan Technological University y de Stephen Whitaker de Michigan Technological University. Bueno, un poquito sobre el capítulo primero. Si no son miembros todavía, se pueden hacer miembro del capítulo gratuitamente en nuestra página. Pues ahí te van a llegar todos los recordatorios de nuestros eventos y nueva información. Si estás interesado en hacer parte de la junta directiva o comité, escríbenos al email y así puedes tomar parte activa en el capítulo. Y quiero mencionar también que hay varios niveles de membresía de la ASA, pero hay una para personas en países de desarrollo y eso incluye todos los países de la habla hispana. Y eso es a un precio reducido de $50 por año. Y también hay una categoría especial para estudiantes que vale lo mismo. Así que eso te trae muy buenos recursos si estás involucrado en investigaciones o si quieres mantenerte al tanto de pues todo lo que hay en la acústica. Aquí están nuestras redes. Pues si no nos siguen, nos pueden seguir ahí y pues ver eventos pasados o anuncios de eventos. Y próximamente estaremos en Discord. Estén pendientes para eso, pero yo creo que va a ser un espacio bien amplio para comunicarse con otros miembros de Spanish Speaking Acousticians. Bueno, les tenemos un recordatorio de la competencia Royster. El premio será $2,500 para estudiantes de posgrado. Y aspirantes deben ser estudiantes de posgrado o estudiantes que van a entrar al otro año al posgrado. Y será un póster, un proyecto de control de ruido y conservación de la audición. Se puede encontrar más detalles en nuestra página. Hay una pestaña que dice competencia Royster, así que chequéenlo. Y aquí están nuestros próximos eventos para que te apuntes. La próxima será al fin de este mes, difusión acústica por Alejandro Biondo. Luego 10 de mayo, acústica forense de salas de concierto por mis colegas David Conant y Henry Ashburn. Y el 31 de mayo, mercado y acústica en México. Y en junio, la historia de superficies de difusión acústica. Bueno, como ya mencioné, este será un webinar con interpretación simultánea. Así que en la parte de abajo de tu pantalla puedes ver una opción para prender la interpretación y cambiar al canal de español si deseas escuchar en español. Y voy a dejar unos segunditos para que hagan eso. Y ya arrancamos con los presentadores. And now I'm going to present our panelists for today. And I'm going to read a bit about their background, and we'll get started with the presentation. First, we have Dr. Andrew Barnard. Dr. Andrew Barnard is professor and director of the graduate program in acoustics at Penn State. He is board certified by INS USA and a certified LabVIEW developer. He specializes in noise control, structural acoustics, carbon nanotube thermophones, and experimental underwater acoustics and marine technology. He previously spent time as an associate professor of mechanical engineering and director of the Great Lakes Research Center at Michigan Tech and at the Applied Research Laboratory at Penn State. In addition to his scholarly work, Dr. Barnard is also an entrepreneur, being a co-founder of 2 startups with former students, NanoSound and SwimSmart LLC. Timothy Havens is the William and Gloria Jackson Professor in the Departments of Computer Science and Electrical and Computer Engineering, Director of the Great Lakes Research Center, and Director of the Institute of Computing and Cyber Systems at Michigan Technological University. Dr. Havens received his Bachelor of Science and Master of Science degrees in Electrical Engineering from Michigan Technological University and a PhD degree in Electrical and Computer Engineering from the University of Missouri. Prior to joining Michigan Tech, he was an NSF/CRA Computing Innovation Postdoctoral Fellow at Michigan State University. Prior to his PhD work, he was an associate technical staff at MIT Lincoln Laboratory. And finally, we have Stephen Whitaker, who's a PhD candidate under Dr. Barnard and Dr. Havens. His research focuses on using neural networks to track and classify acoustic sources. He spent the past 3 years creating real-world underwater and on-ice acoustic recordings with acoustic vector sensors and analyzing the data with modern or novel neural network architectures to best fit these acoustic environments. He works with undergraduate students that help run these acoustic experiments and label the data. And without further ado, I am going to stop sharing my screen so you all can take the reins.
Thank you.
Thanks for that introduction, Zach. So my name is Andrew Barnard, and I don't need to repeat anything that Zach said. I want to thank Zach for inviting us here to speak with your group. I think this is a great opportunity for us. We're really happy to be here. I would try to say hello in Spanish, but none of you real Spanish speakers would actually know what I'm saying. So I'm glad that we have our translator here, and thank you for that opportunity. We're going to talk today about using machine learning for underwater acoustic modeling. And this work was funded by the US Navy through their NEEC program, which is their Naval Engineering Education Center. And really, Stephen Whitaker, our PhD student, has done most of this work. I'm going to introduce the project a little bit and talk about some previous work that led up to this. And then we're going to let Stephen take the reins and talk about all the cool things he's done in machine learning since he's been on the project. For now, I'll let Dr. Havens introduce himself briefly before I jump into the introduction.
Hola a todos. I think that means hello, everyone. It's been a while since I've dusted off my Spanish, so that's all that you'll get for today. So yeah, thank you for having us for this this presentation. This is all you're going to hear from me today is just the hello, as Stephen Whitaker is the PhD student who's working on this and really is doing all the work, and you really want to hear from him. So if there are questions at the end, I'll stick around and would be happy to answer any of them. So thank you for having us.
Okay, thanks, Tim. Stephen, you want to switch to the next slide? So this work started back in about 2015, where we were asked the question, if we were looking at short-range transmission under the ice of acoustic sources that were on top of the ice, what does that look like? And it turns out that's a really hard problem because ice is very chaotic. It's a non-linear medium. Sound doesn't transmit very cleanly through it. And our main area of interest was in the Arctic. So as many of you probably know, with global climate change, the Arctic is opening up, which means there's more activity in the Arctic. So the question that we were looking at was, can we use underwater sensors to understand and track what's going on top of the ice? And we were specifically interested in nearshore regions. So you see a picture here of Utqiagvik, Alaska, which was formerly known as Barrow, Alaska. We were up here for 10 days doing experiments in the northernmost city in the United States. So that was a really fun opportunity with a previous graduate student of mine, whose name is Miles Penhill here. If you look at the bottom image, that is a satellite image, and you can get sort of an idea for where our test sites were. The blue line is the shoreline. The stuff to the left of the blue line is ice, and those little red dots are where we were working. We were about 1 kilometer offshore of the northernmost point in the US. Next slide. So again, this is a idea of where we started this work up in Utqiagvik. You can see pictures of what the ice looks like. And the reason that I put these in here is to give you a sense of scale of what Arctic ice looks like. Usually when we think of ice on water, we think about nice, flat ice. Maybe you think about ice fishing, or maybe if you're from someplace near the equator, you don't ever think about ice at all, which is great too. But in the Arctic, you get these big ice piles near shore, as you can see in the Site 6 picture here. Some of those are actually grounded. So there's about 10 meters of water underneath all of these pictures. And some of those piles of ice actually go down to the bottom. So in addition to acoustic reflector on the surface, in the ice surface, we also have acoustic scatterers with these ice piles, and it's very chaotic, and it changes rapidly with distance, and it also changes with time. So it's a really unique sort of environment to look at acoustic propagation in. And if you look at the slide or the picture in the top center, the Site 1, looking out towards the sea, you can get an idea of what our data acquisition system looked like. We had in-air microphones, we had in-ice geophones, and then underneath the ice, we had hydrophones and acoustic vector sensors, which Stephen will talk a little more about later. So this was a really interesting experiment for us, and we learned a lot about the difficulties of trying to make measurements through nearshore ice shelves using traditional approaches like beamforming and vector sensors. Next slide. We then came back and continued experimenting in Houghton, Michigan. So this is our test site on Portage Lake, just off of Michigan Tech's campus. Zach correctly introduced me as the director of the graduate program in acoustics here at Penn State, but I just started this job 4 months ago. Prior to that, I was at Michigan Tech as well. And Michigan Tech is actually a great Arctic surrogate because we get lots of cold weather and lots of very thick ice. So here you can see an experiment we set up on an inland frozen lake where we had almost 2 kilometers of propagation distance, looking at in-air sources, on ice sources, and underwater sources. And you can get an idea of a graduate student drilling a hole in the ice and see sort of the scale of what that ice looks like. The ice here is roughly somewhere between probably 30 to 50 centimeters in thickness. Next slide. This gives you an idea of some of the data that we looked at originally. So what you're looking at here is you're looking at the acoustic responses underwater of a small propane cannon blast above the ice. So on the leftmost side, you see a spectrogram at the source, and that has time on the vertical axis and frequency on the horizontal axis. As you move each panel to the right, you'll see a similar underwater hydrophone measurement at different distances, 164 meters, 853 meters, and 1035 meters. So you can watch that pulse propagate in time and diminish in frequency as it moves throughout the water column. And the further away you get, the lower the levels are, as you would expect from spreading and absorption. You also can calculate the speed of sound underwater using this. But if you look particularly at that 853 meter mark, you can see there's a lot of reflections and scattering. You get the primary wave arrival, but you also get through ice arrivals. So that acoustic wave that starts out in the atmosphere, couples to the ice, travels through the ice at a greater speed than it travels through the water. So you get a really complicated response when you're trying to track something that's going on top of ice from underwater. And once you get far enough away, in this case, about 1 kilometer away, you start to see very low signal to noise ratios, which make traditional localization techniques very difficult. Next slide. So then we move to moving sources. This is what we were really after. So for our moving sources, we like to use snowmobiles. And Stephen's going to talk about using boats. We use boats as a surrogate for snowmobiles in the summer. And we simplify the problem a little bit, but we started looking at snowmobiles on ice. And you see here the pictures of the snowmobiles we used as targets and the tracks that they were running with 2 measurement sites listed as site 2 and site 3 here. Each of those measurement sites had an underwater vector sensor as well as an in-air microphone to track these snowmobiles. And if you look at the plots on the right-hand side, you can see that the direction of arrival, so the angle of arrival at the vector sensor, roughly matches the GPS coordinates of the snowmobiles. So if you were to look at this sort of squinting a little bit, you might say that was pretty good, that we're actually able to track this okay. But if you look at the standard deviation on the bottom plot, so plot C, you can see that our standard deviation hovers around 45 degrees. So if we have, our space is 0 to 360 degrees, and if we have a standard deviation of 45 degrees, we actually don't have very good localization. And this is a pretty close experiment, on the order of hundreds of meters was how far the snowmobile traveled. So at further distances, this gets even worse. So we asked ourselves, what can we do to improve upon this traditional sort of localization technique? And that's where we started collaborating with Dr. Havens, and we ended up pitching this idea to the Navy MEEC group and brought Stephen on board. And he really took off looking at machine learning and how we can use that to dramatically improve our underwater acoustic localization methods. So with that, I'll hand it off to Stephen.
All right, thank you. So for this webinar, I would like to step through a discussion of our experimental setups that we've conducted over the past years at Michigan Tech before even touching machine learning aspects. And the reason behind this is machine learning does very nicely, but the difficulty in utilizing machine learning in a good manner is by understanding the data set very well. And so if you can understand the data set, then you can utilize machine learning to exploit aspects of your data set very nicely. So I want to initially look at the experiments that we've conducted and then go through steps on how to transform this data set into machine learning data, and then analyze that using machine learning, and then what in the world can be done with the output of this machine learning algorithm. And so we want to, after I explain the experiments, then I can go and step through into machine learning and kind of show the results of machine learning and show what is happening and what can be done and how to utilize machine learning in a good manner. And so this picture right here is just a simple results plot of localizing efforts of an acoustic source. And so this is what Dr. Barnard had mentioned, where we were just tracking a boat that's driving back and forth, and we're trying to localize its position. And using different techniques, we can see that some do better than others. Okay, so before we can get into machine learning, we need to step through all of the experiments or step through the steps on our experiment. So we had a boat drive by our sensor multiple times, and you can see as the orange dots, which are GPS points of the boat is driving back and forth across this river that is at Michigan Tech. And the river itself is quite a complex environment. It's not as complex as an ice environment that was in Alaska, or in fact, we've done experiments out on the ice in this same position as well. But this water environment is a narrow channel. It's a shallow channel, and it's basically a waveguide. You have reflections occurring all over the surfaces, and it creates a lot of non-linearities, a lot of reflections, and a lot of deconstructive interferences. Now, the analysis is all being done with the acoustic vector sensor. So we have the AVS, which is the acoustic vector sensor, is being positioned in one little spot. It's right on the dock off of the Great Lakes Research Center, which is at Michigan Tech. And the one that we use is the Meggitt VS209. And the Meggitt VS209 is a pressure acceleration type acoustic vector sensor that is underwater. And so the acoustic vector sensor has 4 channels of acoustic signals. One of them is the pressure, which is from the hydrophone, and then 3 of them are from the accelerometer, which is a triaxial accelerometer, and it has 3 accelerations along the X, Y, and Z of our sensor. And now what is happening is while the boat is driving back and forth across the river, the vector sensor is passively listening to the boat that's driving by. There are no sonar pings being sent out to track where the position of the boat happens to be. We are simply listening to the spectrum of our boat. And what can be seen is that in the upper left region, or anywhere on the upper area of the sensor, there's not a direct path to the sensor at all. The only way that the signal can actually get to the sensor is by reflecting off the side of the river and then bouncing back into the sensor. So it's a highly nonlinear environment, and a lot of things are making the signal be very disgusting and muddying the signal. So what does the signal look like? Well, this is the response of the acoustic vector sensor. The picture on the left is a spectrogram of the response of the acoustic vector sensor. On the x-axis is time, and on the y-axis is frequency. There's 2 interesting tidbits of this spectrogram. The main one is, or the one that's most noticeable, is probably these horizontal lines. And these horizontal lines are actually noise in our system. It is a 60 hertz shore power noise that's fairly typical when using a 60 hertz sine wave power. It's AC power powering our sensor. And all of these horizontal lines are harmonics off of 60 hertz and muddying and corrupting a lot of frequencies. So this adds some nonlinearity into our environment. And an additional one, the other interesting aspect of our spectrogram are these U-shapes in the spectrogram. And these U-shapes correspond to a moving deconstructive interference pattern. Because when the boat is traveling past the sensor, it is changing the distance to the sensor, and then the environment, the deconstructive environment, is changing. And so the deconstructive interference patterns are moving as the boat is moving as well. And so again, that's another added non-linearity. There's a bunch of analysis that can be done to refute this or kind of clean this up and remove the non-linearities by using a lot of tedious efforts. Or we can use machine learning to figure out these transforms by using machine learning. The picture on the right is just another demonstration showing that we are in a very shallow environment. The depth of the river is around 6 to 8 meters, which is not very deep. It's enough to where the boat's signal can bounce off the surface of the bottom of the river and then bounce back up into the sensor and cause a deconstructive interference pattern. So I want to really explain the processing that we can get to this point right here. It may seem fundamental, just look at a spectrogram, but the processing that we did to get to this point is almost exactly what we do to put it into a machine learning algorithm. So I want to step through the processing that is done in there. So the title of the slide says, the title of the slide says Acoustic Vector Sensor Processing for Machine Learning. It's not particularly the case that it is for exactly machine learning. It is just in general acoustic processing for vector sensors, but we are utilizing this processing for machine learning. And so the initial step that we do is we take all 4 channels of the vector sensor, which is pressure and the X, Y, and Z acceleration, and then transform them into a short time Fourier transform, which is just a spectrum of each individual components. And then we compute the acoustic intensity equation, which is intensity is equal to pressure times velocity. And in our case, we have acceleration. So in the frequency domain, we divide by a j omega to transform acceleration into velocity. So we get the acoustic intensity equation. Now, at this point, we have 3 acoustic intensity dimensions. We have it in the X dimension, in the Y dimension, and in the Z dimension. This is a lot of dimensions that could be passed into a machine learning algorithm. And there's a big cursive dimensionality issue basically in all signal processing, but it is also true in machine learning. And if we transform from Cartesian coordinates to polar coordinates, we can reduce a bit of the dimensionality because we can change from looking at all of the individual X, Y, and Z and just look at the direction of arrival. So in polar coordinates, we have the magnitude of the acoustic signal, which just tells you the strength of the signal. And then more importantly, we have the azimuthal angle of arrival. And this azimuth angle of arrival is the X and Y, it's the X and Z or Y and Z left and right position of where the acoustic source happens to be. In our case, for elevation, elevation is up and down. We don't typically use up and down because we're using a boat that's driving on the water, so it's not going to be going under the water. At least we really hope it does not go under the water. So we can remove the elevation angle, and we can also remove the magnitude because the magnitude is just the strength of our signal, and if there is a signal present, then there is an azimuth angle that is present as well, and there can be a pattern inside of there. So we're going to use polar coordinates for machine learning, and we are going to typically be using just the azigram or the azimuth spectrum for processing with machine learning. And I wanted to show that this picture that I showed previously is the magnitude of the acoustic intensity for our spectrogram right here. So this is just a bit of a callback that this is the processing that was done to generate this picture right here. Okay, at this point, we've done enough processing and enough analysis to actually start using machine learning. So there are a few prefaces I would like to make in here. First off, there is a really nice paper that is presented. There was a webinar by Dr. Aaron Thode about 2 months ago about what this azimuth spectrogram is and kind of an analysis of what can be done with this. I will actually post it in, oh, I can't. Well, I recommend reading this if you want to understand what can be done with the azigram and analysis that can be done with it. In our case, I'm just going to be using it in machine learning. The way that's going to be used is by inserting it into the into a neural network. And by saying putting it into a neural network, I'm going to abstract away a definition of machine learning and point you to another paper or another webinar that was actually 2 weeks ago by Dr. Michael Bianco, which was Machine Learning and Acoustics, Theory and Applications in Source Localization. And he has a really nice paper that describes machine learning in a general acoustics mindset. I don't want to go into depth on that, mostly because there's a lot. His explanation is very, very good, and it's not required to take any of your guys' data sets and use machine learning with it. He explains how machine learning works and what is being done inside machine learning. I would like to explain how to get to that point so that you can use machine learning. And so that is the main focus of what I want to talk about. And finally, this neural network individually, if you are interested in the neural network in detail, we wrote a paper on this topic and explained it in one of our JASA papers. But fundamentally, for this webinar, I want to focus on how to get the process data into the neural network and then what to do with the output of that neural network. What does it even mean? And I want to step through that. So first off, I want to explain how is data passed into the neural network. And in the beginning, we have this azimuthal spectrogram, which is an azigram. It is coined as an azigram. And what we have found that works really nicely is we are windowing the input data so that a good chunk of previous time steps are being included into the current time step of where the current position happens to be. So on the left, we have a pseudo spectrogram of whatever the azigram happens to be. And then on the right, we have the current position of where the tail end of our input data corresponds to. So when we want to go to the next current position, when we want to move on to the next time step, we shift the input by a little bit, and then we shift the current position to where the end of that input data happens to be. This is fundamentally like a Kalman filter where it has a posteriori data and a priori data with it. So the a posteriori data is this backlog of data that is being passed into the neural network. And the reason behind this is that we can have the neural network try to learn if it should be using a Kalman filter based off of the previous data. It can learn when it should incorporate the previous data and when it should be utilizing the new data. If we only pass in the exact time step that we are currently predicting, it doesn't know what the previous time step happened to be. And so there's nothing that can be done with a Kalman filter approach. And then finally, it's just moving on. We move on to a next time step, and then we get our data, and we're predicting the current position. So I've been saying the words passing into a neural network, and this is in a lot of stuff online. They typically say that, but what does that even mean? What does it mean to pass in data into a neural network? Well, if you have your input data, which we know as an azogram, and you are passing it in to a neural network, what is happening is a neural network is a series of matrices or a series of operations. And the input data is being multiplied by all of these matrices, and the weights of the matrices are finding a proper transform to map out to a decent output. Now, there are different types of transforms, but typically in machine learning, you have your transform and then you wrap it around a function, a nonlinear function that adds some non-linearities in there to kind of incorporate nonlinear transforms. Finally, at the end of the neural network, you are outputting data. This is called the predicted value in a neural network. And so the neural network is predicting a value. What is this predicted value? Well, the frustrating part about this is it's anything that you want it to be, which is not usually the answer that I like hearing. So probably means that you don't like hearing it either. But the thing is, you can choose any output data that you want. When you are training your neural network to predict some value, you can simply have the prediction to be exactly that value that you want. In our case, we want to predict the direction of arrival of the noise source. We have input data that is from the sensor of all of these direction of arrivals over these span of frequencies, and then we want to predict just one single direction of arrival. So we are using machine learning to crunch all of these numbers of all of this data into a single value. And if we are outputting the general same idea of angular input in and angular input out, it should map out to a decent prediction. And so if we actually look at the output data and see what it looks like, this is what it looks like. This is a picture in our JASTA paper. It is a time series plot of angle measurements, and it is a comparison of 3 different algorithms compared to a GPS truth. So the GPS truth is this red line that's traveling along kind of like a sine wave. And there are 3 different algorithms that are being predicted. A weighted average is a linear approach of just simply taking all of those angle measurements and then multiplying them by the magnitude of our intensity and then taking an average of that all. And what we can see is that a linear approach does nicely at a linear region. And these low angle measurements from 0 to 50 correspond to an area where the boat is in a typically linear region because it is shooting down the length of the river. And so there's not very many places where there can be a huge amount of reflections. When you get to higher angle measurements in our data set, this is not a general assumption right here. In our data set, when we get to high angle measurements, we are on the left side of our vector sensor, And this is where we are getting a lot of reflections across the river, and we're getting a highly nonlinear environment. And so what happens is the weighted average basically fails at this region. And what we are showing is that in two different types of neural network approaches, a shallow neural network seems to do a decent bit better than a weighted average. And then a deep neural network is actually getting its way to predict into this highly nonlinear region, but it is predicting a very noisy signal. So it's kind of a trade-off, but in a general sense, what we found is that with a deep neural network, it was able to predict better. But I don't really, the point of this webinar is not to explain the difference between deep neural networks and shallow neural networks. The point of the webinar is to say that you have your input data, you have your sensor data, you want to transform it and then push it into a neural network, and then you have the output. If you want to understand the differences between deep neural networks and such like this, please look at the paper that Dr. Michael Bianco presented on about 2 weeks ago about machine learning and acoustics. Fundamentally, can machine learning learn such a complex scenario? Because in that region where there is a huge amount of noise and there's a bunch of nonlinear reflections, is a machine learning capable of mapping out such a highly nonlinear region? Well, we say yes, it does better. We can say that for sure. It does better than a linear approach, which is saying something. And so this picture right here is the same representation of the previous data, but we added a Kalman filter so that we could show more representation of the data over a longer period of time without it being extremely noisy. And we can see that the deep recurrent neural network is capable of predicting at a highly nonlinear region. So that is what I wanted to talk about. And that was for the webinar. So that should be it for me.
Great. Thank you, Stephen, and very, very nice presentation. I think we're going to share those papers in the chat.
Yep.
I am about to share the Aaron Thode paper that was referenced.
Yep.
Okay, you've got that as well.
That is the Azagram paper. It's kind of explaining what to do with a vector sensor data. This is the machine learning introduction by Dr. Michael Bianco. And then this is our paper for our presentation of all of the plots that were shown in here is from this paper.
Great.
And
great.
I'll add that as a sneak peek, Stephen has some really nice under ice data coming out very soon. The paper's just about ready to submit. So watch for that. We'll be publishing that in Sensors Journal.
Great. Well, excellent work here. So these vector sensors, they are very they're really collecting a lot of data here. What are the next steps, I guess, in this project? I know you've got some data coming, but what do you see kind of the future of this and maybe future applications?
I guess a general idea is with a vector sensor is you can take multiple of them together. And in fact, in this paper, we only do direction of arrival. There's another paper that was written that we wrote about using two vector sensors to take both of the directions of arrivals and then position them together to localize our source. And then what happens if you have three? How would you incorporate an array or multiple vector sensors together. And then what Dr. Barnard was talking about in a more nonlinear environment, what about in ice? What's happening in ice?
Sure. Yeah.
I
Great.
think the application space for this is really wide. Could be anything from monitoring the health of infrastructure, bridge pilings, things like that, to situational awareness in the Arctic, which is where we started with this project. But anytime you're using acoustics to, look through a layer, and by layer in our case would be ice, then this might be something that allows you to do that in a different manner than what traditional techniques allow, and in some cases produce better results.
That's great. It looks like we have a question here from Fernando. Neural networks need to be, do neural networks need to be trained to output valid results?
Yes, they do. And the way that they are trained is you have a set of training data. So you have a set of where you're trying to adjust your parameters nicely. And you know where the input, where the boat happens to be, or where your source happens to be. And where, the response of that source as well. You don't know the transform that takes it from the input data to the position that you're trying to track. Training is by pushing in multiple of these. Training is basically taking this input data, running it through the neural network by matrix multiplication, and then comparing it with the predicted value you're comparing with the actual value that it should be. And then you use something called back propagation, which is by adjusting weights such that the predicted value is closer to the true value. And the machine learning paper and webinar by Michael Bianco steps through this a lot more.
So Stephen, why don't you give an indication, a rough estimate of how much training data you used versus what your test data was for the data sets you presented today?
Okay, so the split that we used is, where is it? This data right here is about 10% of the entire data set that we have. I believe that's correct. It might be 10 or 15%. I don't remember exactly what it was, but I'm pretty sure it was 10%. So it was about 900 seconds of test data that we can test on, whereas we had to train on 9,000 seconds of data. So I don't know if that's typical, but it's what we used.
So I'll just add to that. So machine learning, really also takes advantage of something called transfer learning, where most of the algorithms that we use have been seeded with other data sets that may have absolutely nothing to do with the problem that we're working on. And so one way that a lot of machine learning scientists start with the architectures that they build is by building on top of architectures that have been trained by like Google and Facebook and Amazon on data sets that are usually composed of images, say, recognizing birds in images, or, object detection, recognizing people in images. And it's shown that if you start with these networks, which have been trained on millions and millions of datum, that you can then move to train those on your data that could be completely different. In this case, acoustic signatures, and the features that have been seeded with those transfer learned data sets are very useful for starting your neural network off in a good place.
This is great. It looks like we may have a question here in the chat. You chose to disregard the vertical movement of the boat when analyzing data. Can you go into a bit more detail about that decision? How much does the vertical movement due to waves, etc., change the data you are receiving? Great presentation.
I hate to say more than the elevation data did not change very much at all, which is basically why we removed it. When the boat is right next to the sensor, the elevation data, okay, let me step back. Our underwater sensor is about 3 meters under the water. And when the boat is right next to the sensor, that will be the point at which there is a huge amount of elevation deviation. But when it's right next to the sensor, we already have a linear connection, linear transform, or mostly linear transform to the sensor. When we are far away, the elevation angle does not deviate very much. And that is where we're in a nonlinear area, and there's not much benefit to adding the elevation angle into the data for machine learning.
Excellent. And I guess I have a question. How has the kind of interdepartmental collaboration been? I mean, I don't know how familiar you were with machine learning before this project. Maybe you were very familiar, maybe not. And Tim, I don't know how familiar you were with acoustics, or maybe you were very familiar, but is there, how is it kind of leveling the playing field and making sure everyone's kind of speaking the same language?
Well, so I was familiar with acoustics in that I've done a lot of work with coherent signal processing in the past. I was not familiar with acoustic vector sensors, which is kind of a new animal as far as sensors go, and I would say it's more of a sensor fusion problem than your conventional like radar or sonar or array processing type problems, although a lot of the related math involved. I've applied machine learning to all kinds of sensors, including sensor fused problems where we're combining together cameras with radars, with LiDARs, with acoustic sensors. And, you know, we call it the kitchen sink method, where you just kind of put a bunch of stuff out there and take data and kind of see what works well. What I love about machine learning is that it's really showing to have a very broad applicability to just about any problem. And you can even use it in conventional, like physics heavy problems to get a good enough answer for things that typically take, you know, large supercomputers to solve. For example, like finite element analysis is something that, you know, you're solving millions of differential equations on a grid, and, you know, your typical supercomputer problem. It's been shown that you can actually take machine learning and train that on some of the results you've used a supercomputer with. And while you don't get the same fidelity because you're not solving the exact physics equations, you get good enough results, you know, in typical problems to move forward, and you get them quickly. So it's become a great tool for applying kind of across the board and finding new solutions for problems that have been very difficult to solve with first principle physics methods.
Yeah, from my perspective on your question, Zach, the collaboration's been terrific because, you know, I came in at very acoustics heavy, not really understanding any machine learning, and now having worked with Tim and Stephen for the last 4-ish years, can sort of talk my way around the problem at least. But it's really cool to see what these new computational techniques can do in comparison, like Tim was saying, to, you know, what a normal acoustics approach would be for this problem, which might be to set up a 3D parabolic equation with all the geometry of the entire channel, trying to understand the sound speed profiles through the depth of every slice of the channel. And you end up with so much information that you have to put into the model that's really a guess, that your outputs are a guess anyway, even though you have a very high fidelity model. So why not get rid of all that and just go to this machine learning approach where your output is still a guess, but actually it turns out in a lot of cases it's a better guess than what we're doing with the higher fidelity models. So for me, it's been a real pleasure to be able to collaborate in this way, and having Stephen, who really came in from the computer science side and then learned the acoustic side on the fly, has really been fun to watch.
I just want to counter that. I did not know computer science before doing my PhD. I only knew signal processing. And so every aspect of this was fundamentally new to me.
Yeah, well, it sounds like you've been making a lot of progress and, getting a lot of useful data and interesting new skills. So good on that. And I do see we have another question. I know you answered it via text, but just so we can have it in the video in case it's of use to anyone. Tony Hoover asks, how long does this kind of data processing take on reasonable computers such as a laptop? Is it close to real time or much longer?
Yeah, so I put an answer into the Q&A. I typed it in too, but I'll repeat it. So we have a GPU cluster. It's an expensive $100,000, six-figure computer that we use to train these. The training is the expensive part. Once the algorithm is trained, you could probably run this on your cell phone to make inferences and get them pretty quickly.
Okay, great. And if there are any more questions, we've got about a minute left of the scheduled time, and
there's a question in the Q&A, so I'll ask it to you, Stephen and Andrew. You chose to disregard the vertical movement of the boat when analyzing data. Can you get into a bit more detail about that decision? How much does the vertical movement due to waves, et cetera, change the data you are receiving? Great presentation, thank you.
I had already answered that.
Oh, I wasn't listening, sorry.
No worries, no worries. All right, well, if I think we've kind of covered all the bases, I really want to thank you guys again, and thanks for taking the time to get this together and presenting your research. This has been great for us and great for our audience here. So if there's anything else you guys have to say, then now's the time. Otherwise, I thank you again.
Thanks very much for having us. This was great.
Right, thank you.
Yeah.
Thank you.
Bueno, muchas gracias a todos y nos vemos en la próxima el 28 de abril. Al cerrar la presentación va a haber una encuesta and yeah, there's going to be a survey when you exit the session. So please fill that out if you are interested, and we'll see you the next time. Thanks, guys.
Gracias.